So far, we have defined topological spaces and continuous maps. Between these spaces, so next we want to describe continuous maps in terms of limits, which is perhaps in terms of limits of sequences, a more intuitive way of thinking about continuity. So before that, we begin with a discussion on closed subsets. So definition: X the topological space. So a subset Z containing X is said to be closed so if its complement, that is X minus Z, is open in X. So remark: one easily checks the following properties of closed subsets. So 1, the empty set and the full set are closed. 2, suppose we are given finitely many closed sets. Then the union Z1 union Z2 through ZR is closed. And finally, suppose we are given an arbitrary collection of closed sets. Then the intersection is closed. So these three properties are easily checked using the analogous properties for open sets. So that's one remark. The second remark is let S contained in the power set of X be a collection of subsets of X satisfying the above three conditions. Then the collection tau is defined as those u in X such that X minus u, this set, it belongs to this collection S. So then tau defines a topology on X. So here is a simple exercise, also an exercise which is very useful. Let X and Y be topological spaces. So, and let F from X to Y be a map of sets. Then F is continuous if and only if for every closed subset Z contained in Y, the subset F inverse Z is closed in X. So this is an easy exercise, easy and a useful exercise. Okay. So, right. So motivated by the definition of limits of sequences, we have the following definition of closure. Closure of a set. So let A contained in X be a set. The closure of A is defined as follows. So we denote it by a bar. There's those X in X is that for every open U contained in X, which contains X, small x, we have U intersection A is non-empty. So in other words, a point AX in the space capital X is said to be in A closure is if every open neighborhood of X meets A. So it is completely obvious. Let's write this as a remark. It is completely obvious that A is contained in A closure. So next we will prove a series of properties of A closure. So let's begin by proving this lemma. Let A contained in X be a subset. Then A closure is closed in X. So proof. So it suffices to show that X minus A closure is open. So that's by the definition of being closed. So if X is in X minus A closure, so what this means is that is, X does not belong to A closure. So this implies that there is an open set U containing X such that X belongs to U and U intersection A is empty. So it follows that if Y is in U, then Y does not belong to A closure. Because once again, there is an open neighborhood of Y which does not meet A, right? So thus, uh, it follows that so every element Y in U is not in A closure, which is same as saying that U is contained in X minus A closure. So which means, so we have proved that for every, so we have proved that for every X in X minus A closure, there exists an open set U sub X containing X, and U sub X is completely contained inside X minus A closure. So this implies X minus A closure is open. So this completes the proof of the lemma. So proposition, a set A is closed if and only if A is equal to, it is equal to its closure. So proof. So let us first assume that A is closed. So we need to show that A is equal to A closure. So as A containing A closure is obvious. This is just from the definition of the closure. Let us show the converse. A closure is contained in A. So to prove this, it suffices to show that X minus A closure contains X minus A. So this is what we will show. So let X in X minus A be a point. So as A is closed, it follows that U, which is, if we call it X minus AU, is an open set. So thus there is an open set U which contains X and such that U intersection A is empty. So U is X minus A, so then when we intersect it with A, we get the empty set. So this implies that X does not belong to a closure, that is, x belongs to x minus a closure. So thus we have proved that x minus a is contained in x minus a closure. So this proves uh, one side that A is equal to a closure because we have proved that a closure is contained inside A. So next let us prove the converse. So next let us assume that A is equal to a closure. But then by the previous lemma, we proved that the closure of any set is closed. A closure is closed. This implies A is closed. So as a corollary, we get that the closure of closure this is just equal to V closure. So the proof is simple. We apply the previous proposition by taking A equal to B closure. So from the lemma, from the above lemma, A is closed. And then the proposition implies, and so the proposition implies that A is equal to A closure. So when we put A equal to B now, so this implies B closure, right? So here's an easy exercise. Let A contained in B be subsets of X, then A closure is contained in B closure. And another exercise. Let Z contained in X be a closed subspace. Let A be contained in Z. Then A closure is contained in Z. So remark the above exercises show that A closure is the smallest closed subspace containing A. So next we want to define what it means to be dense. So a subset T contained in X is said to be dense if for every non-empty open subset U contained in X, we have T intersection U is non-empty. And we have the following proposition. So let A contain X be a subset and let A bar be the closure of A. Then A is dense in A bar. So here the closure has the subspace topology. So the proof is easy. So we need to show, we just have to apply the definition. So we need to show that if V contained in A bar is a non-empty open set, then B intersected with A is non-empty. So by the definition of subspace topology, we know that uh, V is equal to U intersection A bar for some U open in X. As V is non-empty, so V is the intersection of U and a closure, and V is non-empty. So this implies there is an X in U intersection A bar. So as X belongs to A bar, by the definition of the closure, empty open set containing X meets A. In particular, U meets A. U intersection A is not empty. But now, as U intersection A is equal to U intersection A closure intersection A, and this is V, so we get that V intersection A is not empty. So this proves the proposition. So next we want to prove. So before we prove a certain statement for closed subsets, so we want to see the analogous statement for open subsets. So proposition, let U be open in X and V be open in U. So here, where U has been given the subspace topology. Then V is open in X. So the proof is not hard. It's easy. So let V. So by the definition of subspace topology, By the definition of subspace topology, there is an open set v tilde in X such that v is equal to v tilde intersection u. But now v tilde is open and u is also open, and there is a finite intersection of open sets. So since both v tilde and u are open, sorry, and u are open in X, so this implies v is open in X. So this proves the proposition. So we have a similar result for closed subsets. A similar result for closed subsets. So but before that, we prove a lemma. Let A contain X be a subset. So the closed subsets of A in the subspace topology are precisely of the form Z intersection A, where Z is closed in X. So proof. So the open subsets of A are precisely of the form U intersection A, where U is open in X. So thus, the closed subsets are the complements of these. The closed subsets of A are precisely of the form A minus U intersection A. Now a simple set theoretic check. Set theoretic check shows that A minus U intersection A is equal to X minus U intersected with A. So thus, so writing this A minus U intersection A in this form as X minus U intersection A, we get that the closed subsets of A are precisely of the form X minus U intersection A. That is Z intersection A, where Z is closed in X. So as a corollary, we get let Z be closed in X and let Z1 be closed in Z. So we're giving Z the subspace topology and Z1 is closed in Z. So then Z1 is closed in X. So proof. So by the previous lemma, we have z1 is equal to z intersected z prime for some closed subset z prime in X. And the intersection of closed subspaces is closed. So which implies that z1 is closed in X. Okay. So as a result of this, we have the following proposition. Let Z1 and Z2 be closed subspaces such that X is Z1 union Z2. So a subset Z containing X is closed if and only if Z intersection Zi is closed in Zi for I equal to 1 and 2. And the proof of this is easy using the above corollary. So if Z is closed in X, then by the above lemma, we have Z intersection Zi is closed in Zi. Conversely, if Z intersection Zi is closed in Zi, then it is closed in X. And since as Z, we can write it as Z intersection Z1 union Z intersection Z2 and a finite union of closed sets is closed. This implies Z is closed in X. So finally, we have the following useful. So using this proposition, we have the following useful result about continuous maps. So let's write as a theorem. Let A and B be closed subspaces, be closed subsets of X such that X is the union of A and B. So give both the subspace topology. So let F from X to Y be a map of sets such that when we restrict F to A, so A is sitting inside X, sorry, which maps to Y, So this map, let's call it f restricted to A. Let's denote like this. So that f restricted to A and f restricted to B are continuous. So f restricted to A is a continuous map from A to Y, and f restricted to B is a continuous map from B to Y. So then the assertion is f is continuous. So proof. Let Y prime contained in Y be a closed subspace. So to show f is continuous, it suffices to show that f inverse of Y prime is a closed subspace of X. So by the previous proposition, it suffices to show that f inverse Y prime intersected with A is closed in A, and f inverse Y prime intersected B is closed in B. But now f inverse Y prime intersected with A is exactly f restricted to A inverse of Y prime. And as f restricted to A is continuous, so this implies that f restricted to A inverse Y prime is closed in A. So similarly, f inverse Y prime intersected B is closed in B. So this proves the proposition. This proves the theorem. So this completes the proof of the theorem. So as an exercise, so use the above theorem to show that the map R2 to R given by x comma y goes to minimum of x comma y, and both the maps maximum of x comma y, both these maps are continuous. So we will end here.